you'll have a sensor signal coming back, and there could be other types of sensors for that as well. So now the implication for safety. When we get into higher performance levels, like performance level D, for example, a lot of monitoring has to happen. That's part of safety requirement, right? So it's called diagnostic coverage. And to get this diagnostic coverage of the equipment, you need to monitor certain things. So for example, within a valve manifold, what could be built in there is, for example, a pilot control valve, where you want to assure that a valve won't start up not just electrically but also pneumatically by blocking the pilot air to that valve. And now you want to measure that. Now you would need to monitor the pressure for that to know that there's no pressure in providing a pilot signal to those directional control valves. So within this valve terminal now, things could be integrated into it, like a pressure sensor, for example. We could put an exhaust valve in the valve manifold as well. Again, integrated some sensor technology into that to get some feedback through the network to know that there is no pressure in there. And this all kind of adds up to the, to creating all the requirements needed to achieving that certain performance level. So when we talk about the safety related part of a control system now, so now a network solution could, that valve terminal could be part of the safety related part of the control system with its integrated sensors, monitoring for, again, presence of pressure, maybe monitoring for the position of a spool in a valve, monitoring for the position of an actuator. So all that together can help mitigate these risks, these hazards. And I think this network technology is going to be one of those technologies that could help minimize these things by ensuring that safe operation.
It's about making that data available to the PLC, to the operator, to know it's there.
Absolutely. So, Brian, as a system and controls manufacturer, you must also have some other thoughts on this area too, right? I mean,
you bet. We've gone through this risk assessment and hazard analysis. We've identified some needs to add layers of functional safety on top of the machine. I just hear dollar signs. Boom, there's more cost going into that. As this machine builder, I've got a customer that wants to maintain minimal cost to upgrade these systems. You talk about different technologies. How else does that impact not just the cost, but what other benefits come from some of those technologies that you're adding on to this machine?
Right. So, sure, there's gonna be some increase in product cost, but if you consider the time it takes to do installation for something like this, now let's look at like a traditional way of doing safety for let's say safe exhausting. You may have an exhaust valve rated for safe application, has some redundancy built into it. Now you want to control that in a traditional manner. You may have a safe output block or a safe relay. You are hardwiring this. There's external wiring. There's time to mount all these different devices and so on. You have to run cables to and so on. And actually, some of these systems could get even more complicated. That controlling an exhaust valve might be one thing, but if you wanted to, for example, prevent unexpected startup, it gets a little bit more complicated. Now you're mounting a series of different valves, having to wire them separately, having to now monitor some pressures in somewhere. Now you have a separate pressure sensor that you have to pull back, and you can have a pretty complicated looking schematic where you're running a lot of wiring, you're mounting a lot of different components and so on. And the benefit of incorporating all that into a valve terminal and using a network, like I mentioned, is that it's it's all from the manufacturer built into that product, right? So the installation is a lot easier. The troubleshooting is a lot easier. Uh, it scales up a lot easier. So I think there's a lot of benefits in using that. Like I said, even though there may be a little higher cost in the component side, I think you're going to see savings. You'll see savings as a manufacturer on the installation when you're initially troubleshooting the equipment, when it's going out the door. The end user, I think, will see benefits when they're running the equipment over the long term. Again,
is there any additional levels of safety? You talk about reducing wires, which has to be a big benefit for the company installing it and then the maintenance team working on it. Having everything connected like this, is there additional checks that the PLC or the safety controller can do to that, the inputs, the outputs?
well, yeah, okay. So if you're running safety over the network, of course you have a safety controller now, right? And on the valve terminal side or on the IO side, you're going to if you're going to do safe shutdown in the valve terminal, there would need to be a safe module in that terminal that would be an endpoint for the safety telegram. So when you're using a network solution for safety, you're going to start with safety devices. There's going to be an originator and there's going to be a target. Those have to be safe in design, right? So there's going to be some redundancy built into those devices. The protocol will use, there's a term called the black channel, but it's basically there'll be a separate application layer that for the telegrams that are sent, the telegrams are going to have more, well, they'll be, let's say, time stamping in them. There'll be more checksums included in them. There'll be higher priority messages. So from the network side, from the safety communication, there's extra stuff built into that to assure that the messages are delivered and that they're not stale and so on. But it's important to know that the infrastructure in between could be standard. Safety is all about the endpoints. So you have a safe originator, a safe target, and then you can now have that safe connection to the device. And when you know that you command that device to shut off, you're going to guarantee it's going to shut off. It's with a very high probability of failure because of all the safety that's built into it.
Frank, you've covered a lot of really good stuff. You've talked about building redundancy into a circuit through valve and valve manifold design, which is huge. And I think, it's very confusing. As a manufacturer, I live in the world of valves, but if you're building machinery, you may not understand the intricacies and complexities of a valve. So I think it's important to really understand the product you're using. And to me, it's like Lego, right? How you build it will determine how it fails, how it stops. And there's all kinds of options manufacturers have built in. I want to address a question that came in on the chat. But one of the things with networks for me is there's cyclic and acyclic data, which is sometimes called process and parameter data. And what's happening here is with a hardwired connection, you don't know what's going on in your valve manifold. But when you network that valve and it's connected to the PLC, there's communication there. So some of the data is stored and can be retrieved, like how many times the valve shifted, right? You can do a cycle count. And some data that is critical can be sent back across the network and used to red flag you that, hey, your solenoid has shorted, or there's a thermal issue, something is overheating. You do not get this benefit when you hardwire. And the last time I sort of evaluated this, 40% of the market was still hardwired. There is a reluctance to migrate to the network connection because of cost. And, people say to me, oh, I don't need the data. I don't know what I do with it. That's great, but there's so much benefit in condition monitoring and predictive maintenance to prevent a line from shutting down. So the question that came in the chat, and I'm shifting gears a little, is can you speak to how implementing appropriate safety, specifically in terms of redundancy and monitoring, can impact reliability? This is huge because for safety, what we want to do, you can buy a standard product out of a catalog. You get a year warranty on it. You can install it on a machine, but the liability is on you as a machine builder to test that product, to say that it's proven in use, that it is reliable. You're taking that onus on if it's a safety circuit. There are safety products you can buy and install, and they come with your declarations of conformity and your electrical certification and your third-party certification. And as a manufacturer, I'm kissing the baby, I'm putting a seal on it that is a safe product, but there's something in the middle. And that product in the middle is suitable for use as a safety-related part of a control system. And what that means is, as a manufacturer, I'm going to test that product and I'm going to give you the rated endurance life, either in mean time to failure if it's electronics, or in a B10 value if it's pneumatic. And what that's going to allow you to do is calculate the probability of dangerous failure for your safety circuit. And we're going to cover that a little bit later on, because there's software that can take the burden of the math away. But in terms of redundancy and monitoring, I'm going to show you single versus two channel at some point in this presentation, or we can talk about that. The redundancy is key in the higher risk categories. It's a requirement. And the monitoring is a requirement of the higher risk categories. And so is reliability. Your mean time to dangerous failure must be greater than 30 years in a high risk scenario. So that is all part of designing to 13849 and going through the standards. And I think this all ties into networks, right? How do I connect all of this stuff? So I think there's a lot, and I was honored to be part of the team that wrote this white paper, part of the technical committee for the NFPA. But when you get into it, you realize just how much complexity there is, right? And different skill sets and different experiences people have had will shape how they look at functional safety, because there is a lot. There's electricity, there's electronics, there's hydraulics and pneumatics and different risk factors. And then you try to integrate safety and you migrate to a network for this predictive maintenance. And then you're dealing with cybersecurity. So it continues to evolve, and there's just a lot there. So I hope, Aaron, that helped a little bit. The standards certainly do lay out requirements for higher reliability. And I love this because we're not selling on price. When we get into safety, we need good quality product that is going to stand the test of time, that is proven in use, that is well tried and tested, and comes with that supporting data. So that's a quick answer.
Thanks, Linda.
Yeah.
The white paper talks about this shift from hardwired I/O over to network-enabled devices.
Yes.
Can you elaborate a little bit on that?
Yeah, absolutely. So to me, when we migrate safety to a network, this is all about being accountable to what is going on in our piece of equipment. So as an example, if you have an e-stop and it's hardwired, how many times did your operator shut the machine off? Why is he shutting the machine off? Is he going out for a smoke break, or is the machine jamming? Do you have a production issue? On a hardwired e-stop, you're never going to know. You're going to have high scrap yield, you're going to have downtime, you're going to have increased cycle time, and you don't truly see what's happening in the machine. You put your safety on a network, you've got now a rolling log of how many emergency stops were performed, how many times the light curtain was tripped, possibly what operator was working on the machine at that given time, what your scrap yield looks like, how long the machine was down for. I mean, there's so much inherent value in that, in breaking that down and fixing your problems. If your operator is shutting the machine off using emergency stop to take a break, that's an issue that you want to address to enhance your performance. If your machine is jamming and you unroot the problem of the e-stop was pressed 16 times, in an hour because the machine is jamming, fix your jam, right? Improve your performance and your throughput. So safety over the network to me is a big step in the accountability for the function of the operation of your equipment. And it doesn't hurt that you have data if OSHA come, to see what's going on in your facility. You've taken steps to mitigate unsafe conditions. You're monitoring your equipment. And hopefully there is cost savings in there as well. through that process.
It's hard to put a price on some of that information when you really need that data at the end of the day. That's great.
There can be, it can be difficult, but I think if you're reducing your downtime and you're increasing your cycle time, you can calculate that cost savings. And I have customers that have robots on a network, and through the cloud, they monitor their energy consumption. And they use those hard data, the hard numbers, to justify adding new capital equipment, adding new people to their facility. They monitor usage. And this is really interesting because years ago, people would say, well, energy's cheap, in North America, so we don't bother. But I think there's more of an emphasis now on sustainability, the environmental thing, energy efficiency, and we try to embed that in products as a manufacturer. And of course, through network components, we're now looking at cybersecurity, right? How do we make these network products safe? How do we prevent unauthorized access to the controls on the machine? And we try to make things easy to integrate. So we've got complexity growing, skilled labor is declining, and there's what I call a collision there of technology. So networks collide with cybersecurity. IT collides with OT. Who's responsible for the cybersecurity on your network? I think there's just a lot of questions with the rush of technology. The industrial revolutions happened every 80 years. Now they're happening every 10 years. We got digital twins. We've got all this stuff coming at us, and we're trying to figure out how to manage it and how to make it all work together. And that is where a lot of this complexity is coming from. And I believe it's going to be a huge focus in the future. What's going on in the US right now with, making America great again and bringing manufacturing back is about reducing costs. We need to be competitive with offshore manufacturing, and we're going to do a lot of that through automation. This is only going to grow. The CAGR on this functional safety market's about 7% year over year. I could see that really growing because as we reshore or onshore and bring manufacturing back, we're going to want to use the autonomous, robotics and different things for either very dirty or hazardous jobs, or where we can take our assets, because we only have fixed resources, limited resources, and we want to put our people into higher tech roles like programming, data analytics, managing these robots. So there's a huge training thing unfolding too. And I'm sorry, I kind of went down a rabbit hole, but there's just so much here that I think we're at this critical junction right now, and it's really exciting. And there's a lot of good things happening and a lot of growth. So I'm really excited about this.
That's great. No, I appreciate it. Response there. Awesome.
Mm-hmm.
Oh, I'd like to bring up IO Link, and it's a different layer of communication than what maybe a lot of us are familiar with. Can you elaborate on what is IO Link as far as safety comes to mind?
Yeah, I can take this one, Brian. So the image on the left is how we used to do things, right? We'd connect our valves, we'd hardwire them in a trunk back to IO cards at the PLC. IO cards can be extremely expensive because once you buy a given manufacturer's PLC, you gotta buy their IO cards, right? They're proprietary to the PLC. And there's a lot of time and labor involved in wiring. And if you have a short somewhere, it's just really cumbersome to try and figure out what's going on. There's no communication, something's not working. You've got to go in and try and figure it out. So this collective wiring methodology is considered old now. I realize a lot of people still have it and it works. It's functional, but I would say it's not the smartest way to do things. Going to a network, as Frank talked about, takes away a lot of that wiring, because what you can do is you can wire, and I'm moving on to the middle picture now, you can wire your valves to an IO block. And that can be industrial Ethernet or IO Link, and you don't have that big trunk of wire going up to the PLC. You don't have to buy the manufacturer's IO cards now for their PLC. This is a much cleaner easier way to wire up, I'd say, the architecture of a machine. And it's cost effective, it's quick. You're using M12 cables, you just plug them into your IO block. With IO Link, it's a little bit easier as well because it's an open protocol. So it's not specifically one type of industrial Ethernet. It's open protocol. So you run your IO Link device back to the IO block, and then you can connect to an IO Link master and run it to the PLC through an Ethernet cable. That's what that middle picture represents. A lot of cost savings in time and wiring and getting components on the network. And additionally, IO Link is plug and play. So if your sensor flops out, you can put another one in, connect it, and the IO block should retain the memory of that sensor. So the IO block is addressed, not the component. It's a complexity reduction and a cost savings, because IO Link is typically cheaper than industrial Ethernet. But this is really, how do you want to set up the architecture of your plant? And there is cost savings to be had here if you understand how this is done. Now, the last picture is something that Festo is actually very good at and has embraced, which is IO on manifold. And instead of going to an IO block, they're able to plug devices right into their valve manifolds, and then Ethernet the valve manifold for communication purposes back up to the network. So none of these are wrong. It's really what works for you. Do you want the data communication for predictive maintenance and condition monitoring, thermal warnings? You know, do you want to track cycle count? Will these things add value for you? We really typically only try to send information across the network if it's critical, because traffic on the network does slow the network down. So there's a lot here in how you can connect things, how IO Link can be a benefit for some machine builders. Some plants don't want to add IO Link in with industrial Ethernet. They want to stay just industrial Ethernet. So I think it really comes down to how much IO you have. If you've got a lot of IO to plug in, what we call field level devices, then IO Link might make some sense, because you've got a lot of IO. Make it quick and easy to connect, decentralize the system, and just plug it all in close to where you need to connect. I hope that.
Is there a safety version of IO?
Yes.
Okay.
So for IO Link, just now, IO Link masters are hitting the market. And we actually have some products in development, output devices, that are IO Link safety. So if you have an IO Link safety master, you can connect safe devices to it, or you can connect devices to it that then connect to SIP-safe and Profi-safe networks. They're not SIP and Profi-safe devices, but this is a step where with the safety master, we can connect to that safety network and not have to make SIP and dedicated protocols in our products. Because as a manufacturer, if I'm making a valve, I need to put a safety stack in there. And I need to certify that safety stack to the ODVA requirements, or the organization that oversees that type of protocol. So it's very expensive. I mean, it can be $1 million to make a new technology. And that has really held the market back from an influx of new products, simply due to return on investment, time constraints, cost of making safety products. And I think with this, we're going to really see that come down. That cost is going to come down. And I think we're going to see more products on the market and an easier integration to safety over network on different, like functional safety over EtherCAT or Profi-safe or SIP-safe type networks. We're going to see an easier migration to those.
Okay.
Thank you for asking, Brian. I got sidetracked and forgot about it.
I'd like to, also add a few things to that, right? I mean, on IO Link Master, so today there's plenty of valve manifolds that connect to IO Link, right? And in IO Link, if you talk about a port type B device, right, that's a device that has a separate power, It's isolated from everything else, and that power was there to drive the valve. So if you want to look at safe de-energizing, for example, there are devices today that are on IO-Link, and they might be like SIP safe or Profi safe devices that you can use the network from the controller to shut down that port type B power in a safe manner, right? So that's not necessarily using IO-Link safety, but it's using either SIP or Profi safe to shut the power down to that device. And I think, and then I guess the next step is also like integrating safety, IO-Link safety into the device, where now you have that device and the IO-Link master, like Linda just talked about, that would have a safe telegram between those devices. And there's also work going on today that's harmonizing, or let's say like a companion specifications that are working with like SIP safety and Profi safe and kind of having a companion spec with that to be able to transfer those telegrams all the way down to the IO-Link safety as well. So there's a lot of exciting new things that are going to come up that are that will bring even more features and more capabilities to these devices on both higher level networks and on point-to-point networks like IO-Link as well. So it's a good time coming up for the topic of safety, and in this area, there's going to be a lot of choices for users and machine builders to work on.
Yeah, it's exciting.
I'd like to break down some of these categories. We've talked safety levels, we've talked performance levels. Help, Linda. How do we organize these and understand these?
I think we've made it more complex than it has to be, really. So you got 4 categories, 1, 2, 3, 4. 1 and 2 are single channel architecture, which is what you see on the left. You got one copper wire connecting your input, your logic, your output. Here, the risk is low, right? Per our risk assessment, we know that performance level A and B, Cat 1 and 2 are your low risk. So the thought here is this is simple, and it's like bungee jumping with one cord. I use this analogy. If that cord breaks, you're in trouble. Same thing with your safety setup. If your contactor breaks or something welds shut, you're not going to have good safe function. There's a risk, an inherent risk, because you've got one wire connecting everything. Category 2, which I don't show here, is also single channel architecture, but there's some test intervals and a little bit of monitoring going on. But typically your products here are well tried and tested. They're proven in use, but there's not a high diagnostic coverage. You're using simple logic controllers. You've got safe function, but it doesn't have the value of Cat 3 and 4 performance level D and E with the redundancy. That's what you see on the right. So what we're doing here is we're showing 2 input devices, 2 logic controllers, and 2 output devices. So you typically don't have 2 e-stop buttons wired to your PLC. What you'll have is an e-stop button with redundant contactors on it. And then you have, the 2 wires going to the logic controller. The logic controllers used in these higher category, more risky scenarios are typically higher value safety type PLCs, and they have 2 circuit boards in them. They're built for redundancy. And then those logic controllers will monitor your output devices. And I think Frank may have alluded to test pulsing earlier. This is where we're monitoring the output. It's like a heartbeat, right? Are you alive? Yes, I'm alive. It goes back and forth. If the output device does not respond to the logic controller, the assumption is there's a fault condition, and the system will open to exhaust or shut down. It'll create a safe scenario. So what we're doing with Cat 3 and 4 is we're adding redundancy in our contactors, in our wiring, in our electronics, and we're monitoring those outputs. So Cat 3 is typically a standard PLC and a safe relay, or a low-grade safety PLC. Cat 4 needs 99% diagnostic coverage. That's the ability of this setup to detect fault. A fault detected in safety is good, right? That's considered safe because we were able to detect the fault. We can shut the machine down. A undetected fault is dangerous. So what we want to do with Cat 4 is detect 99% of the faults that can occur. This is where Aaron's question about monitoring and reliability come in. So the standards, when you're evaluating a machine and you do your risk analysis, you're going to come up with your PLR. And if your PLR says that you need to be Cat 3 PLD, your risk evaluation must end up giving you products. This is product selections critical. You want to be equal to or greater than Cat 3 PLD. So you can go Cat 4, but don't go Cat 2 because now you've got liability. There's risk of injury that should have been redundant. And I want to point out, working with machine builders, a lot of them will say, well, I just make everything Cat 3, right? Because then it's redundant and I'm covered. This is, I'm going to say, the lazy man's approach, because what if it should have been Cat 4? And what if your diagnostic coverage was too low and someone was injured? You really should be doing the risk assessment. You should be doing the evaluation, and there's cost savings there to be had. Because if you don't need Cat 4, you can put in Cat 3. If you can go to Cat 2, you're going to save money on your logic controller, on your components. They don't need to have the same level of integrity as a higher category would require. So having some sound knowledge on these principles is really important. If you're designing machinery and you're trying to save money, put in what you truly need. That's your needs analysis to try and recoup some of the cost you maybe weren't planning on spending for safety periphery. And I have sadly seen machine builders do this type of risk assessment at the very end, and they've had to rip entire pieces of machinery apart and redo them because they missed something that was really critical. And it's absolutely sad. This should be done in the development phase. You do this risk assessment throughout the design. Don't wait till your machine is finished to find out you have a problem. That is, it's gut wrenching because it's expensive. You've wasted time. You got to tear it apart, buy new components. So these categories can be powerful, and I'd like to see more emphasis on this and understanding Cat 3 versus Cat 4 in system design. I don't know if I've missed anything. There's a lot here. Between the single channel and the two-channel architecture, there's some things required in the standards, like common cause failure. We want to use components that meet common cause failure, meaning the redundancy does not fail for a common reason. We want the high diagnostic coverage, the ability of the system that you're checking and monitoring to detect faults. All of that is in the standards as part of selecting your components and choosing good quality parts for your safety circuit.
Actually, if I may also add something to that, Linda, that was great. I've also seen customers too that, well, they have a tendency that maybe if I could get a safe exhaust valve and a control for it, and all in a Cat 4 environment, I will always just exhaust air, right? And that's not always the best way to handle a certain task, especially if depending on what the risk assessment shows and what the category shows that you can pursue. So for example, if what you need to do is prevent unexpected startup, for example, there are ways to do that fairly easily and stuff in a category 3 environment where you don't have to exhaust air. And when you're ready for the machine to go back in operation, it just starts right back up because you're just putting it back in motion, right? But if your first thought is to always use a Cat 4 means of exhausting air, that air is exhausted. It takes time now for the machine to recharge. It's a delay. It's unnecessary delay. It could be an unnecessary waste of compressed air, right? So there's a sustainability impact on it as well. So yeah, I think that using the standards, everything that we've put into the compendium for safety, this would help, I think, customers kind of go through that and make them realize that there's other methods than just, exhaust air all the time. And, and you'll see benefits in your equipment on saving air. You'll see benefits on response time of the equipment and so on. But it all depends, again, on the assessments that are done and what kind of categories you need to pursue for, the safety categories you need to pursue. So.
Are you also seeing more people taking control of pilot pressure as a means of achieving safety as opposed to dumping all your supply pressure?
I still see most customers going the dump route.
Okay.
Yeah.
We do have a way to do it with pilot. I know Festo does as well.
We do too, yeah. And that's what we're trying to also mention, is that is an alternative out there, that assuming it's suitable for the proper risk assessment, right?
Correct.
Yeah.
No, I agree. There's lots of options, right? These are pieces of Lego, and how you build will be,
Right.
part of achieving safe function.
So let's step into this process here. I'm a machine builder. I've gone through my risk assessment, hazard analysis, and I follow this equipment, and I put it on, and it just works like it's supposed to. What do I do to test that? Something's going to break. A wire is going to be damaged eventually. How do I test for that?
Great question, Brian. I'll take this because that chain is my infamous weak link. When you build a safety chain, you have your input, your logic, your output. We should be calculating vertically and horizontally the load on that safety circuit. You can't put too many components on because per the standards, you derate your safety circuit. So there's that. You want good integrity, high quality components that meet the category requirements that you're trying to achieve. Validation, to me, is one of the most important and often most overlooked part of functional safety. In fact, Control Design Magazine did a study a few years back now, and something like 20% of people said they don't validate their controls on their machine. The intention in validating your control system is to show that it operates as intended. You're checking that you've met your category and your performance level. And this is where I've seen some people catch some really bad mistakes in the machine they've designed because a fresh set of eyes has gone through and done the validation of their controls and a risk assessment and said, hold on, your diagnostic coverage is too low. You need to modify what you've done here. So the validation is done in several different ways. It can be done through analysis. It can be done through testing. And I think if you're interested in this, 13849-2, which is an ISO standard, is the validation of a control system. And it's 90 pages of how to do this. And it gives you fault exclusion criteria for different types of components. It goes into really extensive detail. This was harmonized into 13849 in 2023. I'm gonna guess 2023 or 2024. They consolidated part 1, safety related parts of control systems, and part 2, validation, and they put it into one document. I still defer back to the 2012 version because I just think they've done such a tremendous job in helping the machine builder break this down. And so, if you're going to do analysis, there's deductive and inductive reasoning and testing that can be done. Fault event trees, FMEAs, failure modes and effects analysis, fault injection testing. Create a fault. How does your machine fail? Shut the power off. Did it fail safe? Did it fail as you intended? Why would you build a piece of machinery and not do validation? I don't understand, because to me, this is so critical.
That's great. Yeah, so many machine builders, and we catch ourselves in that. You test the product, you test what it's supposed to do, but do you test what you're not supposed to do to it? To press that stop at the wrong time and disconnect a sensor, disconnect the actuator, and see what happens. Yeah,
absolutely.
There in order to take care of that.
And I think, Brian, this is becoming more complex because we're starting to see the use of microprocessors, semiconductors, autonomous equipment, things that aren't mechanical. You can't take them apart and figure out if something's going to fail, why it failed. So there's, no real prescribed safety architecture for some of this stuff. We're just starting to write into the standards all of this new technology. And that's why the machinery directive that we know and love, 2006 42 EC, is going to be appended and modified in 2027 to add in all this new stuff. Oh, look at that.
Let's get into that.
I set myself up, didn't I? Okay, so this new EU regulation is coming out. It's not a directive anymore, it's a regulation. And what that means is the machinery directive had to be adopted by every member state country in the European Union. This regulation goes into effect and becomes law across Europe. So 2023-1230 will become law as soon as it's taken live, January 1, 2027. And the idea behind this regulation is to fix the gaps, we'll say, in the machinery directive. So the machinery directive was great about, shipping into Europe. And I'm talking about Europe a lot because this machinery directive is a very broad, all-encompassing standards that came to the United States and were adopted partially by ANSI. But in Europe, and if you're shipping to Europe, you've got to comply with these laws. There were gaps, right? And you weren't allowed really to use certain types of semiconductors in functional safety. And there were no guidelines on how to calculate the mean time to failure for electronics. It wasn't really well defined. So with this new regulation, there's some things happening. So new technology was included, new best practices were added, and new requirements for the manufacturer to provide more endurance life data, B10 values, mean time to failure values, and to make available more data so that machine builders have the tools they need to design safe machinery. We're trying to make it simple. So there is a library that manufacturers make called a VDMA library. And what we're doing is we're loading our products in there. So if you're building a piece of equipment and you want to take, a light curtain from Pills and maybe a controller from Siemens and maybe Festo Zavofa as your output, as an example, you can pull down the VDMA library and import in these products. Parker has a VDMA library, Festo does, most manufacturers do now. And instead of sitting there and trying to calculate the life expectancy, the mission time of a component, the longevity of a component, you can pull into software, which I think, do we have a slide on that next, Brian? I'm kind of getting ahead of myself. Yeah, I thought we were going to cover this. So on the left is a picture of Sistema. Sistema, a lot of people use because it's generic and it's free. And you go in there and you import the manufacturer's libraries and you find your products and you put your safety circuit together. On the right, I'm showing you what this looks like in Pascal, which I think is software owned by Pills, and it does a really good job. You pull in your components, your input, your logic, your output, and you can see at the bottom, it's not a great photo, but it shows you if you've achieved the performance level you set out to achieve, if these three products have the integrity, the diagnostic coverage, and the capability to meet the requirements of performance level C or D or E or whatever it is you're trying to do. And it will calculate the probability of dangerous failure for that safety chain. And as a functional safety engineer, you can do this mathematically, but it's painful, it's time consuming. So a lot of machine builders will migrate to some form of software, and there's lots of different ones. I think Siemens has one. I mean, there's tons of them out there. Most PLC manufacturers offer something like this, and you can download most manufacturers' libraries. The DGUV in Europe has a website, and they post all the manufacturers, and you can go in there and just download our product libraries, which will help hopefully make machine design easier. At Parker Hannifin, I've built one for our pneumatic portfolio, and I'll be working with the Motion Systems group to add content to that. So we're, hoping to expand what we have available in the market, but there is a lot out there today and it's continuing to grow.
And I certainly software packages, all of them give a level of documentation, professional documentation to that machine builder too.
Yeah, you're required if you're building machinery to do a risk assessment. Now, a risk assessment should be done by the machine builder, but also the person installing it has to reassess the safety of the machinery. And the reason for that is when you move equipment, you're disconnecting things. You've got new power coming in, new mains, you've got grounding you've got to think about. So anytime you move machinery, it should be reassessed. And some machine builders will provide their risk assessment to the person purchasing equipment. Some machine builders don't. So if you're going out to buy equipment, understand what is provided and included. A technical file for a piece of machinery is a legal requirement in Europe. It's becoming pretty normal in North America, and there is a lot that goes into that technical file. This is one part of proving that you've tried to mitigate risk, but there are the requirements for your FMEA, your testing on these components, your essential health and safety requirements, a checklist for those, the operating instructions or manual for that piece of equipment. There's a lot, and there's reference materials out there that will tell you what goes into a technical file. But in Europe, if somebody's injured, you have 24 hours to produce all of that documentation. So if you're building machinery, you need to really get this together and have good materials available quickly for your equipment. You are liable and responsible for it. If you're shipping into Europe, and I'm going down another path here, but there's so much information. If you're shipping to Europe, you have to have a representative body in the European Union who takes responsibility for your piece of machinery. Someone in Europe has to be accountable for your equipment. In North America, we go to CSA and UL for our electrical stuff. Europe does a self-certification, a CE mark. And with that comes a declaration of conformity. Parker Hannifin, conform to the requirements of the European Union, and I can ship my machinery overseas and market. So every country has different rules and laws, and they will all make up part of this technical file based on where that machinery will reside when it's completed.
Well, Linda, you've been in this world for a long time and you know a lot of the standards. I'm learning every time I talk with you or anyone in industry.
So am I. It's every day. Constant challenges.
There's all these resources out there. I spoke earlier about how to find them. NFPA has lots of opportunities or lots of connections through industry, whether it's manufacturers or different safety softwares like this or calculation softwares. I want to reiterate to reach out to the NFPA for that. Denise will have her email address up here later in the presentation. But she can connect you guys, anyone listening, to the right experts like Linda and Frank, others in industry that have might be machine builders themselves, and also reference back to the white paper that was put together. The last 3 or 4 pages of it, I believe, are all different acronyms and big glossary and then different references, all the different standards available. So let's get out our crystal balls here and let's take a look into the future here regarding functional safety on this industrial machinery. We've talked about different hardware that's being put together with additional sensors. You've got inputs on valve terminals that were just outputs. We're going over IO-Link or different protocols to communicate these signals back and forth. Cost, I talked about as a machine builder, it all sounds expensive, but then if you look at the larger picture, that the installation might be reduced because single wires where it used to be a big trunk of wires headed back. It's just setting the stage here for what's around the corner. What does a manufacturer need to do to stay up with technology, keep relevant product going out to machine builders like myself, right? Many on the call today too. What do machine builders need to know to use the right parts and not overspec a lot of items in there? So a lot to unprocess or unpack here, but put it out to both of you. How do we go forward with the future here?
Wow. Well, Brian, let me say that first of all, great summary on the conversation today. I think that was really good. I just see safety becoming more and more ubiquitous in automation from the control supplier's perspective. So controllers that come from almost any control supplier now will continue to incorporate safety into their controllers more and more frequently. The use of safety networks in these controllers will become more and more frequent, I think, and they'll get pushed down to even the cheaper and the smaller, mid-size and even smaller size range of controller. I believe we'll have safety in the future go more and more often. What that'll do is that's going to drive on the target side, the component side, I think more safety devices and elements, and that's just going to bring the prices down. And as that comes now, I think for the pneumatic manufacturers, and we're just going to see more devices. It's going to be more common to have safety built into, for example, a valve terminal where you can now control various zones in the valve terminal, for example, right? In a very easy manner, you could have a group of directional control valves in the terminal. You would be able to shut down in a safe manner a small group of them, have the remaining valves, let's say, continue to operate. It's going to give manufacturers, machine builders like yourself, some more flexibility on how they deploy these systems, and so you could just have a small section where an operator might walk in to add some material to the system, but the rest of the machine could be running fine if it's not in that safe area. This could all be done with one manifold, let's say, with multiple safe zones in it, for example. I talked about before about air pilot control. We did talk about that to be able to shut down the air pilot control and monitor that. It's going to be easier to put exhausting in a valve manifold where you can just have a section also exhausted in a safe manner if that's the right subcategory that needs to be followed. You're going to have more purpose-built products. So we talked briefly about pulse testing before, for example. The purpose of a pulse test is, for that cable that's going to be connected from a safe output to a device that you want to be safe, like a solenoid coil, a solenoid valve. And you want to make sure, especially when you get to the very higher performance levels and categories, that there's no short circuits. You don't want to short, especially a real dangerous fault would be a short to positive, where you can't detect that. And you shut off your device, and something else is turning it on. For example, pulse testing eliminates that. It goes dark for a very short period of time, milliseconds. While it does that, the electronics in the output check to see that there are no shorts, and then it brings the power back up. Now, that's fine, but over the years, more frequently in the past, I would say with certain devices, that pulsing could have a negative effect on the coils. Some coils pick that up, and you could even hear an audible tick in some cases, or you could see a flash of the LED on the valve. It's not good for the product. What this new technology is coming forward with that we're going to see in the future, we're going to have more purpose-built solutions for things like that, where you'll build an output driver specifically for a group of solenoid valves. You won't, and you'll design around that, for example, where you'll eliminate that type of pulse. So you're going to also improve the longevity of coils and for pneumatic devices as well. And I think also, the future, this technology scales up really well. So I think in the future, if you implement network-based solutions for safety, if you do it on a small scale, on a small machine, for example, you need to scale that up. It's really easy to do because you're just going to add another member to that network, another element in the program, and your safety program will check that. But it's going to be easy to replicate in the safety program. It's going to be easy to replicate on the network. So the technology also scales up very well, very easily as well. So that's what I see in the future. I see more and more integration from suppliers like Festo, like Parker, simply because it's just going to be more ubiquitous from the controls manufacturer, and we'll follow that lead and create better and easier solutions for machine builders to implement.
Great, thanks, Frank.
Well, on my end, Brian, I certainly don't have a crystal ball, but Industry 4.0 was about networking machinery and getting machines communicating. Industry 5.0, they're calling cyber physical systems. And what we're talking about now is human machine interface, collaborative robots working with people. So what I'm projecting is an increase in knowledge. We need to bring people, into the fold of functional safety and to understand this new autonomous stuff that's happening in the plants. I see an increase in adoption. Nobody's running their plants with steam and electricity anymore. We've moved on. And I think as the revolutions continue to unfold, new technologies come out, I think people will adopt. Some are slower than others, but I think the adoption adds value. And I think all of these new things that are coming out are going to become more accessible and more cost effective. And I think manufacturers are going to make available the documentation and data, the safety related part of control systems require these B10 values for pneumatics and mean time to failure values for hydraulics. And I'm predicting the emergence of more new technology. We're not going to stop now. We're on a roll. We're going to try and harmonize a lot of what's happening. And I think integration is going to have to become easier. So, I think we'll see a day where we can connect robots to a plant much faster than we do today. And I'm in the middle of integrating one at Parker, and it is not a simple process to add a robot controller or a guided AGV or AGW, whatever you want to call them, these autonomous pieces of plant machinery easily. So I think this is all going to be necessary to support cost pressures from offshore markets as we onshore and build, up our manufacturing base again. And I think the skilled labor shortages are going to intersect with the advancing technology, and we're going to have to really do some serious training and help people build their skill set. And I don't see robots replacing people. I see robots helping people do more complex tasks, right? So we've got a lot of people retiring in industry too. I heard some crazy stats the other day that 11,000 people retire a day from the manufacturing sector. And only 4% of millennials and Gen Zs want to work in fluid power. And it's absolutely disheartening because it's an amazing career to embrace new technology. I think that there's a perception out there that's wrong. I've done this my whole life. I absolutely love it. I would encourage my children to do it. And I think there's going to be a lot of manufacturing coming back, given the tariffs and the cost increases and all of the things that are happening. I think there's so much potential here.
That's great. Yeah, you talk about the technology continuing to grow. It feels like I've been in fluid power my whole professional life, whether that was a user buying components and now more or less picking them and working with them. I talked to my daughter, who's 15, about getting into fluid power. She says, "Dad, that doesn't sound fun." But then we talk about the different technologies and how it's everywhere. The beginning slides showed different industries, whether it's wind energy, automotive, everything. It doesn't matter. There is an element of fluid power, and then the overlaying electronics and communication on top of all that. Fundamentally, fluid power hasn't changed since they originally were running water down canals and stuff, right? It's still there. We control it differently. We monitor it differently every day. As this technology, like I said, overlays over top of those sensors and those actuators and pumps, we gain more information back, and it's what we do with that, whether it's a safety aspect or just total data that's pulling in. improving processes, improving the efficiency of the machinery. That e-stop that they hit 10 times in one shift, was it the smoke breaker? Was it the cardboard jam? Time and time again. It's really neat. I agree. We've got to encourage young ones to get into the industry. We're constantly interviewing salesmen and engineers that haven't been in the industry, and they're qualified salespeople. And you start to show them some of this technology, and it's just everywhere. It's around the corner. It's wonderful. Very happy to be in fluid power and connected to the NFPA. NFPA has a lot of initiatives to continue to grow fluid power from elementary, middle school ages into college, and all throughout that professional career. I believe we have a little bit of time for question and answers.
And there is a question in the chat or in the Q&A box. I'll read it out and you guys can help Benjamin out. He says, we also found that pulse testing of the module outputs can be problematic. Our solution is to pulse test only our inputs checked and blocked by our internal controller, and to continuously monitor the outputs in operation to sense any internal or external shorts. Do you agree that this satisfies the high level of DC?
So the diagnostic coverage, if you want to achieve performance level E, is over 99%. I'm not sure how fast you're monitoring. I think that might have something to do with it. And to be honest, I'm not sure if that's going to achieve a performance level E requirement. For D, it's much less. If that's your goal, that could also be. I think that could possibly be a proper scenario. So of course, I'd have to be more aware of everything in the application to really say if that's great or if that's good or not. But like I said, 99% diagnostic coverage, performance level E. The pulse testing is literally checking for shorts every several hundred milliseconds. So it's quite rapid on the diagnostics and continuous. Linda, do you have a comment on that? You seem like you want to.
Yeah, every 15 milliseconds or so, you've got that heartbeat, right? So it's pretty fast. You can adjust the timing in the PLC on some products if you've got a function block integrated. So I have seen people trying to manage their output devices, and they've struggled with the function block piece of it. Usually you can adjust the timings either in the function block and or in the controller, and that might help. I don't know the problem you're referring to, and I'm certainly not a controls engineer, but we do have a team at Parker that work in the field that are controls engineers. So if it's a piece of Parker equipment, we can go out and help you integrate it. Other manufacturers have similar individuals that are there to help you integrate their products, whether they're field-based or they're tech support. So I don't know what your product is, but that might be an avenue to solve some of the challenges you're having. But I think, to Frank's point, Cat 4 requires greater than 99% DC. Cat 3 is greater than 90. And it is a requirement legally to monitor the output. So if you're doing that, you're probably fine. But again, we'd have to get into the weeds with you to really give you a proper, safe response.
Pulse testing is usually it's a parameter within the device product itself that in some products it can't be adjusted, in some it can. And the dark channel usually could be anywhere from like several hundred microseconds to 15 milliseconds or something like that. It's extremely fast. Again, so that provides 100% diagnostic coverage, or 99.99, because it's happening continuously. It's really hard to say if what you're doing is equivalent to that, if that's the performance level you need to reach or category.
Thank you. Looks like we have another question in the chat. Let me pull it up. Bob is asking, he says, currently as fluid power engineers are retiring, the speccing in of products has gone to the control engineers. Valves, pumps, motors have become outputs on a PLC. What I've seen and run into is controls engineers are trying to design circuits and run into issues because it doesn't function as expected. Any comments on that from the panel?
So I know Bob, and Bob is really good at what he does. Bob is a sales rep with a controls background. And yeah, you're right, Bob. There is a lot of issue there with people trying to understand circuits. And now you look at a fluid power schematic, right? If it's open, you have flow. You look at an electrical schematic, if it's open, there's no current. There's no contact being, they're backwards. And it's very confusing. And you get a young person looking at a system and there's electricity there, there's fluid power in there, there's microprocessors, semiconductors, there's robotics, you know, it's not surprising people are struggling. And I think now more than ever, you need to work as a team to solve challenges, to understand system design, work with your manufacturers, understand the function of their valve and the features and benefits that it offers, and turn to the manufacturer's resources, controls engineers, and their sales reps for guidance. You know, a lot of people like to work in a silo and they'll pull stuff from the internet and they try to figure things out, but use your resources. This stuff is getting more complicated. And if you run into issues and things aren't functioning as expected, we want to solve those challenges before you built the piece of equipment, ideally. That's what functional safety is, designing out risk before you have to take additional measures and implement safe function. So the 3 requirements are design out the risk, then protective measures, and then technical measures of labeling the hazards on the machine. But yeah, you know, utilize the people around you. This is so complex and I learn every day. I've been doing this 18 years and there's just so much I don't know. And if there are standards that are relevant and applicable to your machine, make the effort to read them. Some of them are 140 pages and you know, it's dry, right? It's written like a legal document, but there's so much value in understanding what you're required to do. And that will help you spec your product as well, so you know what you're looking for. I don't know if that's a good answer, Bob, because it was sort of an open question, but right. Yeah, any thoughts, Frank or Brian?
I don't have any thoughts on that, Linda. I think you really covered that pretty well. I actually I did have a thought about the pulse test question from before, maybe just to address that again. I do have another comment on that. What happens if you're trying to drive a solenoid valve or something with a pulse test? There's a certain capacitance that's in there that kind of fools the test, and then it'll often fail the test because of that capacitance. And that's a common thing that has happened. A lot of people work around that by putting a diode at the end device. So you're really just now looking at what's on the wire and not inside the device. However, I do recommend if you're going to do that the manufacturer should provide a fault exclusion for what's in that device. So if the assumption is that you're going all the way to the, let's say it is a valve manifold and you're going through the power connector of that manifold all the way deep into the coils, a manufacturer could provide what's called a fault exclusion that says, you know, we're going to guarantee that inside our product there's not going to be any chance of a short to open or short to 24 or short to 0. And it's going to be because we check all of our castings and we guarantee that there's no metal burrs or anything inside, and we have distance between the traces on the boards are large enough and so on, and there's not going to be any kind of chance for that. And that's a declaration that the manufacturer provides for what's inside that device. And then if you have that, then theoretically, then you could maybe use a diode to mitigate some of the issues that might happen on the pulse test due to like high capacitance inside the device that holds up the energy that doesn't. So when the pulse test goes dark, it still sees some energy there because of that. So just another thing to look at. And then again, the topic of fault exclusion, we didn't really cover that in the product, but that does exist from several manufacturers.
Thank you, Frank. We've had another question come in, this time from Aaron. Can you guys speak to major challenges or differences between the pneumatic and hydraulic functional safety, specifically considering Cat 3, Cat 4 requirements?
I can take that.
Yes, please speak to pneumatic. I'll try to speak to hydraulic a little here too.
Okay, so as far as I'm concerned, from a functional safety perspective, it doesn't matter. It's an energy source, right? Hydraulic, pneumatic, electromechanical. What we're trying to do is prevention of unexpected startup, fault mitigation, and monitoring. And we want things to fail safe, right? Whether that means hydraulic fluids dumping back to tank or you're exhausting your compressed air. Where I see a difference is in the data if you're doing calculations. So the mean time to dangerous failure of a component is the B10D life divided by the number of operations. Basic mathematical formula. B10D is the point at which 10% of a sample lot of product have failed. So as a manufacturer, I'm going to cycle test my mechanical product until it fails. I'm going to come up with a switching cycle life, and I'm going to give that to you to calculate your mean time to dangerous failure. So if my B10 value is 25 million switching cycles, you're going to divide that by 0.1 times your number of operations. You're going to come up with the mean time to failure of a component. Pneumatically, we give you B10 values because these products are typically mechanical, and we cycle test them until they fail or leak or break. And we use a standard, I think it's 19978. Don't quote me on that. There's a test standard out there for product that we have to follow. We have to test it given humidity and temperature, and the point of failure is determined by the leakage rate. It's all documented in the standard, and there's a standard for valves and a standard for cylinders, etc. If you're buying product that is electronic or hydraulic, you will not get a B10 value. You're going to get a mean time to failure, dangerous failure value from the manufacturer, because in the standards, hydraulic products, I guess, are considered more reliable, and they're allowed to assume a given number of operations before failure. So they can do that math for you, and they can publish the mean time to failure value. This is very confusing for people trying to size stuff. You got two different mathematical numbers. What do they mean? B10 is a switching cycle life. Mean time to failure accounts for the use of that product. So from a functional safety perspective, that's the biggest difference I see in doing the calculations for safe function for equipment. To me, the concept of keeping the user safe, monitoring the equipment, and trying to mitigate danger by designing out hazards and protecting hazards that remain are the same in my opinion, unless either of the panelists have had other experiences.
Brian, Frank?
Yeah, just, comparing the two and the fundamentals of the different technologies, the air being compressible or gases being compressible, the fluid in a hydraulic system has a level of compressibility, but it's nothing to the degree of airs and gases. Frank talked about exhausting the air, or exhausting a circuit. It's obviously something you never intend to do in a hydraulic circuit. To vent to atmosphere. In hydraulics, quite often we talk about wind down on a pump or a motor. You hit the e-stop and you want all energy to be dissipated or isolated. Sometimes that means it's killing the diesel engine or shutting a system down like that. So you need to calculate into that wind down time of the engine, whether you've got a intake shutdown or a choke on the intake, or it's a blocking valve with some redundancy into that. It's reviewing each of those hazards to get that performance level required, and adding sensors back into that. At the end of the day, it's just calculating each of these. True differences between pneumatics and hydraulics are a little difficult to nail down each of those, especially when you're considering the Cat 3s and Cat 4s. We upgrade presses quite often, and each press has a different end result on the components that are out there. The standards give different examples of hydraulic circuits. You look at those, but then you need to apply components to those circuits or to those individual components there. And each of them will impact that calculation at the end of the day. Flow rates come into it, the CV of a pneumatic system, or the overall pressure drop of a hydraulic circuit. You could have inappropriately sized components that are creating additional hazards into that. That's where you need to continue to do that testing and validation to confirm that your design reinforced the true nature of the machine at the end of the day.
I want to touch on what you said, Brian, about stopping a machine. There's different ways to stop a machine. Safe stop 0, safe stop 1, safe stop 2. Safe stop 0 is like pulling the plug, energy is instantly killed. Safe stop 1 keeps some energy to the actuators until a safe shutdown can be initiated. And the other safe stop leaves power on. Much like fluid, an empty machine is considered a safe machine, but not always. If your machine is holding a load, killing the power or draining the energy can pose a dangerous condition, which flies in the face of what we think of when we think of safety. There are requirements if you want to keep entrained energy in a system to have a secondary means of stopping, blocking, or holding a load. So when you're looking at system design, you have to understand the function of the machine. And this to me is what makes this so complex, right? You can't just say, well, we're going to cut power on everything. What if that actuator holding the load drops? And then you get into a discussion about load holding and what type of valve to use. I mean, there's a whole world of stuff there. But I think you really got to understand how you want a machine to fail. And if you design it so it fails safe, you're doing a decent job. You know, what you use normally open or normally closed contactors. Well, what do you want to happen if someone accidentally energized the machine? What do you want to happen if the power were to be disconnected? And think about what state your valves would end up in. How would your machine fail? And we want that machine to fail safe at the end of the day. So there's no right or wrong answer on how you design a circuit, as long as it creates a safe state. I think it's the right way to look at it, more than trying to figure out what is it I'm supposed to be doing, because every piece of equipment is different, especially retrofit or MRO.
That's great. Thanks, Linda.
All right. Well, on behalf of NFPA, I'd like to thank each of our experts here on our panel, Frank, Brian, and Linda. Thank you very, very much for the presentation today. And thank you for all the hard work. Yeah, the hard work and effort that you guys put into the functional safety white paper. So both are available on the NFPA.com website. I want to thank everyone for attending today. If you've got questions, we ask that you funnel them through me. I am your NFPA membership manager, Denise, and there is my email address. This concludes today's webinar. Again, if you've got questions, reach out to us. I can get these to our experts and or any of our engineers that are on our standards development, et cetera. So thank you all for attending. You'll be, as I said earlier today, there will be a link sent out to everyone so that you can listen to the webinar at your leisure or share it with people there at your companies. So again, thank you and have a great rest of your day.
Thank you.
Thank you, Denise.
Yep.
Thanks, everyone.
Yep.
Thank you.
Brian,
Bye-bye
good
now.
job. Bye-bye.
See you guys. Bye.